All right, welcome back. In this lecture, we begin a review from distribution theory. This information will be very useful because we will be working with distributions throughout our study of linear regression. For example, we'll be working with univariate distributions, multivariate distributions, joint distributions, and marginal distributions. We will need to understand various characteristics of these distributions, such as mean structure and variance-covariance structure. We will be working with joint distributions of data, and in order to make statistical inferences about model parameters using estimators calculated from the data, we will need to derive and understand the sampling distributions of these estimators, and not only their marginal sampling distributions, but also their joint sampling distributions. Here are the topics that we'll be covering. We'll be talking about expectation. We'll then talk about covariance and variance. We'll talk about correlation and then stochastic independence. And we'll talk about the relationship between stochastic independence and correlation. We'll also talk about the normal distribution, not only the univariate normal distribution, but also the bivariate normal distribution, as well as the general multivariate normal distribution. So the first topic we'll be talking about is expectation, and so let's get into it. And so we'll first define what we mean by expectation in the context of a single random variable. So let x be a random variable with sample space denoted by script A, and with probability density function, or PDF, if x is continuous, or probability mass function, PMF, if x is discrete, which we will denote by lowercase f. So lowercase f is the PDF of x if x is continuous, and it represents the PMF if x is discrete. Now, let lowercase g be some function of the random variable x. Then g of x is a random variable itself because it's a function of a random variable. Now, the expectation of the random variable g of x is denoted, as you see here, capital E for expectation, with g of x inside brackets or parentheses. And it's defined in the following way, depending upon whether x is a continuous random variable or a discrete random variable. If x is a continuous random variable, then the expected value of g of x, or the expectation of g of x, is the integral over the real line of g of x times f of x. So again, f of x is, in this case, the PDF of the random variable x, and g of x is the random variable whose expectation we're after. On the other hand, if x is a discrete random variable with sample space script A, then the expectation of g of x is the sum over the entire sample space of g of x times f of x, where in this case, f of x is the PMF of x, the probability mass function, and again, g of x is the function of x whose expectation is we're after. Now we can also talk about expectation in the context of two or more random variables. We'll focus on, in this slide, on the definition of expectation when we're dealing with two random variables. So let x1 and x2 be random variables with joint sample space script A, and with joint PDF if x1 and x2 are both continuous, or PMF if x1 and x2 are discrete, denoted by lowercase f. So again, lowercase f is the joint PDF or the joint PMF, depending upon whether the two random variables x1 and x2 are either continuous or discrete. Now again, let's let g denote some function, in this case of both x1 and x2, then the expectation of the random variable g of x1 and x2 is denoted, as we might expect, capital E for expectation, with the function of the random variables in brackets or parentheses, so g of x1 comma x2. And again, the way that we define the expectation depends upon whether we're dealing with continuous random variables or discrete random variables. If we're dealing with continuous random variables, then we define expectation using integration. All right, so we've got some calculus going on here. And so this would be the double integral over the entire plane of g of x1 comma x2 times f of x1 comma x2. And if x1 and x2 are discrete random variables, then we would we define the expectation as the sum over the entire joint sample space, script A, of g times f. So g of x1 comma x2 times f of x1 comma x2. So expectation is an averaging process. All right, because we're calculating here in both cases, the continuous case and the discrete case. We're calculating weighted sums, or in this case, weighted averages. Okay, because the weight factor is the PDF. All right, the weight factor gives the probabilities, the probability masses in the discrete case, or the probability densities in the continuous case. So expectation can be thought of as an averaging process. So that's how expectation is defined. We really don't want to have to do much calculus in this course if we can avoid it. All right, and even doing these summations and things, if we can avoid doing those kind of calculations, we'd like to as well. And in particular, calculating expectations using the PDF or PMF. And so to try to facilitate this, we can look at some very useful properties of expectation. And once we know these properties of the expectation operator, then we really won't have to get down to the level of doing integrations or summations involving the PMF. So let's let x be a random variable and let a and b be constants. Now notice that we haven't specified whether x is a continuous random variable or a discrete random variable. We don't need to do that because these properties hold regardless of which of the two kinds of random variables we're dealing with. So x is just some random variable, and a and b are constants. Then the following properties hold, the following equalities hold. The first says that the expected value of the constant b is just that same constant b. So the expectation of a constant is equal to that same constant. So that's a very simple property, and it's very straightforward to show this, but it's very useful. The next property says that the expected value of the quantity, the new random variable a times x plus b, is equal to a times the expected value of x, and then plus b. Now in words, this says that the expectation of a linear transformation of a random variable is equal to that same linear transformation, but of the expectation of the random variable itself. So a times x plus b is a linear combination of the random variable x. And this is saying that the expected value of that linear transformation is equal to that same linear transformation, but applied to the expected value of x. So a times the expected value of x plus b. All right, next, let x1, x2, and so forth up to x sub n be a collection of random variables, and let a1, a2, and so forth up to a sub n be a collection of constants. Then the following equality holds. The expected value of the sum I going from 1 to n of a sub I times x sub I is equal to the sum, I going from 1 to n, of a sub I times the expected value of x sub I. So what this is saying is that the expectation of a linear combination of random variables is equal to that same linear combination of the expectations of those individual random variables. So the sum, I going from 1 to n, of a sub I times x sub I, that is a linear combination of the x sub I random variables. And so what this property is saying is that the expected value, the expectation of that linear combination, is that same linear combination of the expected values of the individual random variables. So it's equal to the sum, I going from 1 to n, of a sub I times the expected value of x sub I. Now, this property is stated in terms of a finite number of random variables, but the result holds more generally for an infinite number of random variables as well. Okay, next we're going to look at covariance and variance. So let's first define what covariance is, and we're going to define this in terms of expectation. So let the random variables x1 and x2 be jointly distributed according to some distribution. The covariance of x1 and x2, which is denoted by this notation here, COV, and then as an argument to the covariance operator, we have x1 comma x2. So that's how covariance is defined. That's how it's denoted. It's defined in terms of expectation as follows. So the covariance of x1 and x2 is equal to the expected value or the expectation of the product x1 minus the expected value of x1 times the quantity x2 minus the expected value of x2. All right, so covariance can be thought of as the average value of that product. The average value of x1 minus its expected value times x2 minus its expected value. Now, the covariance of x1 and x2 can also be calculated using the following formula, which we might call a computational formula because it's easier to compute in many situations. So the covariance of x1 and x2 is equal to the expected value of the product x1 times x2 minus the product of the expected value of x1 and the expected value of x2. So this is typically easier to calculate because we only have to take one difference. We only have to take the difference between the expected value of x1 times x2 and the product of the expected values of x1 and x2. If we look back on the previous slide, we see that we actually have to take two differences in that expectation. So in many cases, this computational formula is going to be easier to use. Now, this formula is equivalent to the definition formula, and it can be derived very easily using properties of expectation. So make sure that you can derive this formula from the definition using the various properties of expectation that we've covered so far. So that was how covariance is defined and easily calculated. Now we need to look at some useful properties of covariance that are going to make our lives a lot easier as we think about the distributions of estimators and things like that. So property 1 involves the covariance of a random variable and a constant. So let x be a random variable and let a be a constant. Then the covariance of x and the constant a is equal to 0. Now what this is saying is that the covariance of a random variable and a constant is always going to be 0. Okay, let me say that again. The covariance between a random variable and any constant will always be 0. Now, property 2 is useful. What this is talking about is that the order that we list the variables in the covariance operator is irrelevant. It does not matter. The value of the covariance between two random variables does not depend on the order that we list them in the argument list. And so let x1 and x2 be random variables. Then the covariance of x1, x2 is the same as the covariance of x2, x1. So again, the covariance is symmetric in its arguments. In other words, the order that we list the variables in the argument list is irrelevant. Property 3 is useful. This deals with variance expressed in terms of covariance. And so let x be a random variable. Then the covariance of a random variable x with itself, the covariance of x, x, is equal to the variance of that random variable x. And so in words, this is saying that the covariance of a random variable with itself is the variance of that random variable. Property 4 deals with the covariance of two linear combinations of random variables. So let x1 and x2 and y1 and y2 be random variables. So we have 4 random variables here, x1 and x2 and y1 and y2. And then let a1 and a2 and b1 and b2 be constants. Then the following decomposition of the covariance of two linear combinations holds. So if you look at the left-hand side, we have the covariance of two linear combinations of two random variables each. So the first linear combination of two random variables is a1 times x1 plus a2 times x2. Okay, that is a random variable itself. The second linear combination we're looking at of two random variables is b1 times y1 plus b2 times y2. Now, that linear combination is also a single random variable. It involves two random variables, but taken all together, it is a single random variable. So just keep in mind that covariance is always dealing with two random variables. Now, how those random variables are represented depends on the situation, and they may individually deal or involve more than one random variable each. But when you look at the calculation that's being done, for example, in this particular situation, we're calculating two linear combinations of two random variables. They both resolve to one random variable each. Okay, so the covariance of a1 times x1 plus a2 times x2 with b1 times y1 plus b2 times y2 can be decomposed into, or according to the right-hand side of that equation. So a1 times b1 times the covariance of x1 and y1 plus a1 times b2 times the covariance of x1 with y2 plus a2 times b1 times the covariance of x2 with y1 plus a2 times b2 times the covariance of x2 with y2. Now, this decomposition can be extended to linear combinations involving any number of random variables for either of these two linear combinations. Property 5 deals with the variance of a linear combination of random variables. So let x1 and x2 be random variables and a1 and a2 be constants. Then the variance of the linear combination a1 times x1 plus a2 times x2 can be decomposed into the following expression. a1 squared times the variance of x1 plus a2 squared times the variance of x2 plus 2 times a1 times a2 times the covariance of x1 and x2. Now this is expressed here in terms of a linear combination of two random variables, but this result can be extended to linear combinations of more than two random variables. And then finally, property 6 deals with the variance of a linear combination of random variables that have zero covariance. And so this is a special case of property 5 in the sense that we're looking at variables that are pairwise uncorrelated. All right. It's expressed in terms of n random variables, though. So let's take a look at this. So let x1, x2, and so forth up to x sub n be a collection of random variables such that the covariance between any pair of these random variables is 0. And then let a1, a2, and so forth up to a sub n be constants. Then the variance of the linear combination of the x's, given by the sum I going from 1 to n of a sub I times x sub I, the variance of that linear combination is equal to the sum I going from 1 to n of a sub I squared times the variance of x sub I. All right, so we've defined covariance and we've looked at some of its properties. Now we're in a position to define correlation. So let the random variables x1 and x2 be jointly distributed according to some distribution. The correlation of x1 and x2, which is denoted by cor, C-O-R-R, of x1 comma x2, is defined in the following way. The correlation of x1 and x2 is equal to the covariance of x1 and x2 divided by the square root of the product of the variance of x1 and the variance of x2. Now this is equivalent to the covariance of x1 and x2 divided by the product of the standard deviation of x1 times the standard deviation of x2. Now let's look at how to interpret correlation. So correlation is a measure of the strength of a very particular type of relationship between two random variables. In particular, it's measuring the strength of the linear relationship between two random variables. Now, correlation will always be between -1 and +1. And so if you're ever calculating a correlation and you get something either less than -1 or greater than +1, you better go back and check your work because you've made a mistake. Because mathematically, correlation is always between -1 and +1. Now, the sign of the correlation provides information about the type of linear relationship, and the magnitude of the correlation, in other words, its absolute value, provides information about the strength of the linear relationship between the two random variables. So let's first look at types of linear relationships. So a positive correlation indicates that a positive linear relationship exists between the variables. Now, this is a linear regression class. Let's speak in terms of explanatory variables and response variables. And so a positive linear relationship means that as the explanatory variable increases, the response variable tends to do the same thing. It tends to increase. And as the explanatory variable decreases, the response variable would tend to decrease. On the other hand, a negative correlation indicates that a negative linear relationship exists between the variables. And so this would mean that as the explanatory variable increases, the response variable tends to do the opposite. It tends to decrease. And as the explanatory variable decreases, the response variable would tend to increase. Now, the magnitude of correlation gives us information about the strength of the linear relationship between the two variables. the closer the correlation is to either -1 or +1, the two extreme values that correlation can take on, the stronger the linear relationship between those two variables. The closer the correlation is to 0, the weaker the linear relationship. A correlation of 0 indicates that no linear relationship exists between the variables. But this does not mean that there is no relationship at all. It just means that there's no linear relationship between the two variables. A correlation of either -1 or +1, the two extreme values that correlation can take on, indicates that a perfect linear relationship exists between the variables. Another way to say that is that the linear relationship is deterministic. There's no random component to it. In other words, there's no deviation from the line of the data points in the vertical direction. So let's take a look at some examples of what we're talking about here. We'll look at some graphics and look at scatter plots of data that have different levels of correlation. And so the first scatter plot is a plot of 25 data points. These XY data points have a very high correlation. The correlation between X and Y in this data set is 0.9928. So it's a positive number, and so that indicates to us that there's a positive linear relationship between the two variables. And the fact that it's close to 1, 0.9928, that tells us that it's a very strong linear relationship. And we can see that from the plot. All right, we can see if we were to fit a line through that data set, okay, and here's another plot that does that, we can see that there's very little variation, very little deviation of the points off of that line. And when we talk about deviation of points off the line in regression, we're talking about the vertical distance, okay, of the points from the line. And so you can see here that when you have a very strong correlation, a very high correlation, the points are going to fall very closely to the line through those data points. There's not going to be much variation off of those data points from the line. Now here is another data set. Again, we have a very strong correlation. The correlation is close to -1. It's equal to -0.993. It's negative, so that indicates to us that there is a negative linear relationship between the two variables. And the fact that the magnitude of the correlation is close to 1, so the absolute value is close to 1, that indicates that it's a very strong linear relationship. And if we were to fit a line through those data points, then you can see once again that because that correlation is so strong, right, that linear relationship is so strong, there's not much vertical deviation of the points off of that line. All of the data points fall very close to that line of best fit. Okay, here's a scatter plot, again of 25 data points. In this example, the correlation is not nearly as large. It's 0.5872. And so that would be considered a moderate correlation. And you can see here that when we fit a line through that data, there's a lot more deviation of the points from the line in the vertical direction. So the points don't fall nearly as close to that line as they did when we had that high correlation of around 0.99 or -0.99. And so we see here that the weaker the linear relationship, the more variability there is in the vertical direction about the underlying line. Okay, here we have a scatter plot of 25 data points where the correlation is -0.69. So again, not nearly as strong as it was when the correlation was -0.99. And so when we fit a line to that data, you can again see that there's much more variation of the data points from the line. All right, here is a scatter plot of 25 data points where the correlation is very close to zero. All right, negative 0.072. Now, because the correlation is negative, that would indicate that there is a negative linear relationship between the two variables, but because it's so close to zero, that linear relationship is really, really weak. All right, and so, in fact, if we were to fit a line to that data set, you can see that there's much, much more variability of the data points from the line. And you can tell that by looking at the scale on the left-hand side. The scale on the vertical axis is much larger than it was on the other plots. And so, in fact, just looking at those data points, if we didn't know the value of the correlation, or if we didn't know that the line of best fit has a negative slope, it would be very difficult to determine at all what kind of what direction or what type of linear relationship we're talking about. In fact, we may even question whether there's any linear relationship at all. Okay, here's a scatter plot of 25 data points where the points fall perfectly on a straight line. In fact, if we fit that line to the data, we see that the line goes through every data point. The correlation here is equal to +1. All right, that indicates then that there's a perfect linear relationship, in other words, a deterministic linear relationship between the two variables. All right, there's no deviation of the data points off of the line. And then finally, here is a scatter plot of 25 data points where the correlation between the data points is -1, and so that indicates a perfect negative linear relationship between the two variables. All right, a deterministic linear relationship with a negative slope. There is no variability of the data points off of that line, and so that's what makes it a deterministic or perfect linear relationship. Okay, next we're going to talk about stochastic independence. This is a very important topic. All of the procedures that you've learned up to this point, more than likely, have been based on an assumption that your data constitute a random sample from some population. And one of the characteristics of a random sample is that the observations are stochastically independent. So let's define this. So let the random variables x1 and x2 be jointly distributed according to a distribution with joint probability function, or PDF, lowercase f, and with marginal PDFs f1 and f2 respectively. The random variables x1 and x2 are said to be stochastically independent if and only if the joint PDF can be written as the product of the marginal PDFs. Notationally, what that means is that x1 and x2 are stochastically independent if and only if their joint PDF, which is lowercase f, evaluated at x1 and x2, is equal to the product of their marginal PDFs, f of 1 evaluated at x1 times f of 2 evaluated at x2, and this equality holds for all x1 and x2. So two random variables x1 and x2 are stochastically independent if and only if this equality holds for all x1 and x2. Now, determining whether x1 and x2 are stochastically independent using the definition requires that we know the joint PDF of x1 and x2 as well as their marginal PDFs. Now, if we don't know the marginal PDFs, we obviously cannot use the definition to determine whether x1 and x2 are stochastically independent. The following result is similar to the definition, but it does not require knowing the marginal distributions first and is therefore easier to use. So we'll call this theorem 1.1. let the random variables x1 and x2 be jointly distributed according to a distribution with joint probability density function, or PDF, lowercase f. Then x1 and x2 are stochastically independent if and only if the joint PDF can be written as the product of a non-negative function of x1 alone and a non-negative function of x2 alone. That is, the random variables x1 and x2 are stochastically independent if and only if the joint PDF, f of x1 and x2, can be written as the product g of x1 times h of x2, where g is a function of x1 alone and it's always non-negative, and h is a function of x2 alone and it is also always non-negative. Now, the nice thing about this theorem is that we don't have to derive the marginal PDFs of x1 and x2. All we have to do is to be able to factor the joint PDF into two functions as shown here. And so it becomes a factorization problem, which is much, much easier to do. All right, next let's look at what we're going to call Theorem 1.2. Let x1 and x2 be stochastically independent random variables. Let g1 be a function of x1 alone and g2 a function of x2 alone. Then the expectation of the product of the functions is equal to the product of their expectations. Notationally, what this is saying is that the expected value or the expectation of the product of g1 of x1 times g2 of x2, so it's the expectation of a product of functions of random variables, is equal to the product of the two expectations. So the expected value of g of x1, or g1 of x1, times the expected value of g2 of x2. Now, the assumption here is that x1 and x2 are stochastically independent. This type of decomposition holds when the two random variables are stochastically independent. If they're not stochastically independent, then we cannot decompose the expected value of the product in this way. All right, so if the two random variables are not stochastically independent, this equality will not hold. Now, let's look at a corollary to that theorem. And so we'll call this, let's see, the theorem was Theorem 1.2, and so we'll call this corollary 1.2.1. So let x1 and x2 be stochastically independent random variables. Then the expected value of x1 times x2 is equal to the product, the expected value of x1 times the expected value of x2. Now, the proof of this corollary follows directly from Theorem 1.2 by letting both g1 and g2 be the identity function. So g of x1 or g1 of x1 is just equal to x1, and g2 of x2 is equal to x2. All right. Now we have Theorem 1.3. Let x1 and x2 be stochastically independent random variables. If that's the case, then the covariance of x1 and x2 is 0, and therefore the correlation of x1 and x2 will be 0 as well. So again, if x1 and x2 are stochastically independent random variables, then the covariance and the correlation between those two random variables will be 0. Now, a question that I have for you is this: is the converse of Theorem 1.3 true? All right, and so I want you to think about that, and we can have a discussion about it. But this type of question may show up on an assignment or an exam, so I do want you to think about this. Now, what would the converse of theorem 1.3 say? Well, this is what the converse of that theorem says. Let x1 and x2 be random variables such that their covariance and correlation is 0. Then x1 and x2 are stochastically independent random variables. Now that's the converse of theorem 1.3. My question to you is this statement true? Is it the case that if we have uncorrelated random variables, that those random variables are necessarily stochastically independent? So that's the question. This is the converse of theorem 1.3, and the question is this true?